So, welcome back to the course on architectural design of ICs. So, in the last class we have seen that squaring circuit, how we can do, then again multiplication using squaring circuit, where it will be used, when it will be beneficial, that means what is the architecture, that we have seen in the last class. Okay. So, after that we have discussed that the till now whatever multiplier architecture we have discussed, that is based on this integer, or that means they are considering the fact that the number is not constant, they are unknown to me. But in DSP system, what we know that the numbers are basically known from the beginning as the coefficient values there, or the two-layer factors for FFT, or the coefficient, that means the filter coefficient values there for FIR filters or IR filters or any of these filters, the function, that means the corresponding values, they are fixed for any particular specification. So, from the beginning we know. So, after that how we can design one circuit which will be optimized, as the number is from the beginning we know. So, at that time can I get the benefit of that whenever we will design the multiplication operation for those DSP system. So, that we will see in today's class. Okay. So, to start with that, okay, so here the topic is basically reconfigurable constant multiplier design based on this common sub expression elimination algorithm. So, to start with this reconfigurable architecture of this constant multiplier design, I have to I will discuss what is constant multiplication, where it is used basically. Then we will come to the fact that what is the meaning of reconfigurability, or this what is the meaning of reconfigurable architecture and why I need to design this reconfigurable constant multiplier, and then what is this common sub expression elimination algorithm and how it basically advantages or how it used to design one that means efficient architecture for this reconfigurable constant multiplier design. Okay. So, now let us first initially consider this fact that what I have seen, or what I told you, that suppose I am having one, okay, what is happening? Let us consider I am having one this is my X in. Okay. So, these are the filter coefficient, these are the resistors, okay, and this is the Y out. This is nothing but one 3-tap FIR filter architecture. Okay. So, here you see I need multiplier for doing this 3 multiplication. So, what is happening here? These are the coefficient values, which is A, B and C. So, in most of the case we know that this FIR filter coefficient values that cannot go beyond 1. So, they are basically less than 1 all the time. So, then my first point is that, or the first understanding will be that how we represent the that means the fractional value, suppose 695, 7, 5, something like this fractional value, which is this values is where the values is less than 1, how we can represent in binary number. So, how we can represent? Basically, we can represent in binary. How we represent? That is, suppose I am having the decimal point in this particular location. Okay. So, then I am having this A0, A1, A2, A3, something like this, and B0, B1, B2, B3, something like this. So, if I consider the decimal part at this particular the decimal point at this particular position, so at that time the weight for this will be 2 to the power 0, this is 2 to the power 1, this is 2 to the power 2, this is 2 to the power 3. So, before to the decimal point, whatever is the value or whatever is the point or whatever is the, that means corresponding bits. So, that corresponds to the weight in terms of in the power of 2. But after the decimal point, that the corresponding bit position, which is this B0 to B3, they are also considering the fact that they are also the values are in the power of 2. But here the values are varying in terms of 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, 2 to the power minus 4, something like this. So, that means now if I want to, suppose if I have to represent one 6 to 5 data, okay, or the values which is basically 0.625. So, how I can represent that value? So, this particular value corresponds to what? 0.5. This corresponds to what? 0.125. This 0.25. So, this corresponds to 0.125. This corresponds to 0.0625, something like this. Okay. So, that means now if I have to get these 0.625 values, so this basically says 0.5 plus 0.125. So, that means the values will be something like 0.101, and then if I consider rest of the bit will be 000. If I consider 8 bit to represent the corresponding value. Okay. So, this is the fact how we represent the decimal this fractional value in binary. Okay. So, now this what I said or what we know that in DSP system, this corresponding filter coefficient values, they are mainly less than 1. That means they will be something like this, the values will be something like this. Okay. And not only that, the fact is that all the time it will be known depending on this 3-tap specification of 3-tap FIR filter. So, these values will be known from the beginning. Okay. So, if I known from the beginning, so here what is unknown? The unknown values is what will be my x in. So, that means if I just come to this particular point, so this will be the output for this particular output at this particular point, the output will be A into x in. Okay. So, here the output is B into x in if I just do not consider this register, suppose there is no register. Okay. So, at that time this will be B into x in and this will be C into x in. So, these are the 3 multiplication which I have to do for this kind of architecture or this kind of to implement this kind of circuit. So, here you see one thing is that now A is basically represented by this kind of things, the same for B, the same for C. So, can I write these particular terms, this A x in a different way? I can write. How can I write? So, suppose the values for A that are what? That is 0.625. So, now if I want to add A into x in, so at that time what will be its values? It will be 0.1010000 into x in, something like this. So, means what? This means what? How I can get the corresponding A into x in value? If I just write this particular term, I know that this is the what is the, that means power of, or what is the, that means this values of this particular position, that is 2 to the power minus 1. Okay. So, that means if I just write this a into x in such a way, so that I can get it in a, I can get the results, but in a different, the representation of that can I write it in a different way? I can. So, what it will be? A into x in can be written as x in by 2 plus x in by 4, x in by 8, x in by 16 plus x in by 32 plus x in by 64 plus x in by 128, 1, 2, 3, 4, 5, 6, 7 plus x in by 256. Not only that, so here along with that, what I have to write? What is the bit corresponding bit position for this A? So, this is the A7. So, this is A6, this is A5. So, this will be ANDing operation. Then again, so x in will be ANDed with A4, this will be with A3, this will be with A2, this will be with A1 and this will be with A0. That means what? Now, this particular A into x in operate, that means this particular term or this can be written as this A7 into x in divided by 2 plus A6 into x in divided by 4, A5 into x in divided by 8, A4 into x in divided by 16 plus A3 into x in divided by 32, A2 into x in divided by 64, A1 x in divided by 128 plus A0 into x in divided by 256. Now, if I have to multiply with 0.625, if this corresponding A value is 0.625, so at that time only this will come. So, that means it will be x in by 2 plus, so this will be 0, because what is the values of this? That values is 101 and rest all are 0, right. So, this will be x in by 8, rest all are beta 0. So, that means all these particular terms will be 0. So, only this I require only one particular adder to do this 0.625 x in. Okay. That means what? For these particular terms, though I require how many adder? That means for to do this 8 terms, I need 7 addition operation, but as this number is fixed, so I require only one number of addition operation for this particular case. So, that means the rest of the 6 that I do not require to do. So, that means for this constant multiplication, I can get the area optimization as well as the power optimization on the higher side, as we know this value from the beginning. Okay. So, now this is for A into x in. So, if I just go back to the previous, so how many operation I am having? A x in, B x in and C x in. So, 3 particular terms, this A is different, B is different and C is different, but x in that is common to each of these. So, at that time what I can do? So, if I write this is in a matrix form, okay, considering the fact that each of these is basically 8, right, 8 bit, each of these A, B, C of 8 bit. So, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7 and then 8, right. So, this is for A, this is for B, this is for C, and each of this case, this is, if I consider, this is x in by 2, this is x in by 4, this is x in by 8, x in by 16, something like this, up to x in by 256 for each of this position, where this is basically multiplied with the corresponding bits of A. This particular position is multiplied the corresponding bit position of B. This particular position is being multiplied with or ANDed with bitwise, this is bitwise ANDed. So, that is ANDed with the each of the bit of C. Okay. So, that means this particular, this basically now this forms one 2-dimensional matrix. Okay. So, now if I consider the fact that I know this A, B, C from the beginning, then for each of this multiplication operation, that will be optimized as in the previous case. For this, if this value is 0.625, okay. So, only one this x in by 2 plus x in by 8 I have to add to do this 0.625 into x in. Suppose this value is, let us consider that is 0.5. Okay. So, only x in by 4 I have to do. So, in this way the corresponding multiplication operation which is required here, that will be optimized in a better way. Okay. If I just do the, if I just, that means generic multiplier if we use, so at that time it requires huge number of logic elements or the logic gates, but in this case the logical expression for each of these that are reduced in a great extent. That means I can reduce the or I can improve the performance of this circuit in a better way. Now, what I said, whenever I know that these values are fixed, at that time this can be done. But in some case what happens that I do not know the values. Okay. I do not know the values of this A, B, C, that means these values are not same. I do not know the values of this. So, at that time or the values of this A, B, C, they can change dynamically. So, at that time I need one, or at that time this particular things is needing for one reconfigurable architecture. Reconfigurable architecture means the same architecture can be accommodate the different values of A, different values of B, different values of C. So, how we can design that fact or design one particular circuit where any of the values of A, B, C can be accommodated. So, can I design one such kind of circuit where any of those values of this A, B, C can be accommodated to design the corresponding this multiplier architectures. Okay. So, it can be done. So, it can be done how? It can be done based on the fact that, so when it will take, so at that time you consider the worst case. So, worst case means as for this 0.625 the values are like only 1, 0, 1, rest all are 0. So, that means as only this two particular bit position is 1, that is why there is only these two addition operation. If I want to, that means do this multiplication operation in a shift and add based method. So, at that time when all these positions are 1, so at that time I will get the maximum number of terms over here for the addition operation. So that means as this particular position is, that means each of this is basically ANDed with the corresponding values of A. This particular position is being ANDed with the corresponding values of B. Okay. So that means x in at this for A, what is happening? A into x in, what is happening? That is A7 x in divided by 2. So, A6 into x in divided by 4, A5 into x in divided by 8, then A4 x in divided by 16. So, A5 x in divided by 32. Okay. Then this is A3, this is A2 x in divided by 64 plus A1 x in divided by 128 plus A0 x in divided by 256. The same thing happening for B x in also. So, here what is the change? Only this x in by 2, that is common, only that this particular B is value is changing. So, here it will be B6 x in by 4, then B5, then it will be B4, then it will be B3, then it will be B2, then it will be B1, then it will be B0, and each with multiplied with this corresponding terms. Okay. Each ANDed with this corresponding terms. Okay. That means, if I do not know the values of A, so at that time I have to add each of these particular terms in this way. Okay. So, what will be the architecture for A into x in then? So, A into x in then, it will be something like, we require this AND gates, total 8 AND gates, so this is A7 x in. Okay. So, x in is basically common for all this. If I just say, okay, what is happening? Then this bit is only different, this is A6, this is A5, this is A4, this is A3, this is A2, this is A1, and this is A0. Okay. So, now this is basically divided by 2. So, that means this will be left shift by 1 bit. Okay. So, this will be left shift by 2 bit, this will be left shift by 3 bit, this will be left shift by 4 bit, this will be left shift by 5 bit, this will be left shift by 6 bit, this will be left shift by 7 bit, this will be left shift by 8 bit. Why? Because what I am doing, that is what I am doing whenever I am doing A7 into x in plus divide by 2. So, divide by 2 means that is right shift by 2, right shift by 2 means thus discard the LSB, left shift means increase the, that means power, and that means multiplied with 2, right shift means divide by 2. Okay. Discard the LSB, divide by 2, and that means put one extra bit at the LSB means you are basically increasing the power of 2, increasing by power of 2. So, how many bit position in the LSB you will put? So, that much in the power of 2, that much you will enhance the corresponding magnitude of the bit or the magnitude of the corresponding values. Okay. So, now then for each of these now, so this is ANDing operation, this is not AND gate, it will be one series of AND gate. Why? Because if I consider the xin of 16 bit, so I require A7 will be ANDed with each of these 16 bit of x. Okay. So, this is not only one single AND gate. So, this is a series of AND gate which are basically dependent on the values of x, that means the word length of x. Okay. So, now this particular 2 bit will be, now I have to add in this manner. So, this is nothing but the addition operation, then so this here I will get finally A into xn. So, why I require this addition operation? If I just go back here, you see each of these terms is basically finally added to get this A into xn terms, right. So, here I am doing this final addition, that means these are the partial products generated from this particular ANDing operation. So, after that each of these partial products has been added or summed up to find out the final A of xn. So, this same kind of this particular architecture now it will be followed for B, the same architecture will be followed for C. That means, at that time only the change will be at this A7, A6, A5, A4. Instead for B it will be B7, B6, B5, B4. For C it will be C7, C6, C5, C4, something like this. So, that means for A into xn, so how many of this AND gate that means this series of AND gate operation I require? Okay. So, they are of 8 numbers, right. And for this summed up, how many adder operation I require, addition operation I require? They are 7 number. Okay. If I consider that means for A, B and C, 3 of these particular coefficient values. So, that means at that time how much require to implement this particular circuit? This particular circuit where I need to do this AXin, BXin and CXin. So, how many of this addition operation and this ANDing operation I require? Into 3. That means total 24 number of ANDing operation I require and 21 number of addition operation I require. Okay. So, this is to implement in a generic way, where and why is that? Here what I am considering, I do not know the values of A, B and C. So, at that time I require this 24 number of ANDing operation and 21 number of addition operation to perform this AXin, BXin and CXin on that particular circuit. Now, my point is that, and this kind of structure is basically known as reconfigurable structure, okay, where I do not know, that means this value corresponding this A, B, C values. So, now my point is that can I optimize this circuit in such a way, or optimize in this circuit means can I reduce these numbers more. So, reducing these numbers more means I can save the power as well as the area. Okay. So, can I reduce it? If I can reduce it, then what will be the method or how, what will be the approach, how can I reduce the corresponding numbers in these particular terms. So, how can I do that? So, in this regards people have developed different algorithms to do this optimization in these numbers. Okay. So, one of them is this binary common sub expression elimination algorithm. Okay. So, what happens there? What is the meaning of this common sub expression, and then what is the meaning of binary common sub expression elimination algorithm? So, that we will see in the next class. So, thank you for today. If we have any doubts regarding this, so then please let me know via discussion forum. Thank you.